Hello everyone, I'm David, and I'm going to be telling you about the type-independent resource theory of local operations and shared randomness, which you can read about in these three works, which were done by myself and the co-authors listed here. So I'm going to introduce a unified framework for non-classicality and common cause scenarios. These are scenarios where there are various parties, let's say two, and neither party can causally influence the other party. But there might be some common causes in the past that mediate correlations between the processes that these parties observe. The most common such scenario is the Bell scenario. But in any experiment where all the operations are done at space-like separation, this will be the causal structure. And this lets us unify a lot of ideas like entanglement, non-locality, steering of states, steering of channels, Bob with input steering, measurement device independent steering, teleportages, which are a kind of resource for teleportation, distributed measurements, and the list goes on, as we'll see. And in particular, I'm going to show you that all of these are different manifestations of a single kind of resource, non-classicality of common cause. And that's in contrast to the usual idea that entanglement and non-locality are inequivalent kinds of resources, and that steering is also some inequivalent kind. I'm going to show they're all the same kind of resource within this resource theory. Okay, so what are the types of resources that we consider? Well, a resource in this talk is going to be a no-signaling quantum channel distributed among various parties. So let's focus on the bipartite case for simplicity, although everything generalizes easily. So here's the two parties, and here's what a resource looks like. Each party has some inputs and some outputs. And the type of a resource is determined by the nature of its input and output systems, namely whether they're quantum systems, classical systems, or trivial systems. So let's introduce some graphical notation to distinguish these three. A trivial system will have no wire. A classical system will be represented by a single wire. A quantum system will be represented by a double wire. And if I don't want to specify whether it's trivial, classical, or quantum, but leave it be any of these possibilities, then I'll draw it with a dashed double wire. So you can see as we go increasing in complexity of the system, the wire type gets increasing in complexity as well. Okay, so what does a bipartite quantum state look like, for example? Well, it's an object on two quantum systems. So there's two outputs and no inputs in this case. If you have a state, you can use it to do something interesting. So for example, Alice and Bob might perform local measurements on their state. A measurement is a channel from a quantum system to a classical system, where that system's value encodes the output of the measurement. So here we see Alice and Bob doing local measurements on a state, which converts the bipartite entangled state into some potentially correlated joint probability distribution over two classical systems. If instead they choose their measurements from a set of measurements depending on some classical setting value, then we get essentially a Bell scenario, where an entangled state is converted into an object which, if we view it as a black box, it's something with classical inputs and classical outputs, and these are often termed no signaling boxes, or non-local boxes. And these are essentially conditional probability distributions, P of AB given XY in the bipartite case. If the measurements are done just by Alice but not Bob, this is the steering scenario. So depending on Alice's choice of measurement here, she steers Bob to one of a set of ensembles where the elements of that ensemble are labeled by this classical outcome. And so this type of object, which has a classical input and output for Alice and a quantum output for Bob, has been termed a steering assemblage in the literature. Another thing you can do with an entangled state is teleportation. Namely, Alice takes some input system that she wants to teleport to Bob. She measures it jointly with her half of the quantum state, and then gets some classical outcome which she communicates to Bob, who does a correction operation. And if they choose these three operations appropriately, then they can implement an effective identity channel from this input to this output. That's called quantum teleportation. You might be saying, hang on, David, this kind of process clearly has a cause-effect relationship between the parties. So how can you fit it in your framework? And you're right, we can't. But if we look just at the process before this classical communication occurs, then what this nice paper here showed was this process here, without the communication, contains all the relevant information for teleportation. So let's just look at these processes, which now are in fact no signaling quantum channels. So it's an object of this type. It's got a quantum input and a classical output for Alice, and a quantum output for Bob. These have been termed quantum teleportages. So that's how we're going to fit teleportation into this framework. If both Alice and Bob do these local joint measurements like this, now we have an object which has quantum inputs and classical outputs, So it's a measurement type channel, but it's distributed among the parties. So I'll call it a distributed measurement. And then there's a bunch of other types of resources which have been studied in the literature. I won't mention them in detail here, but there's channel assemblages, which is the generalization of steering to channels rather than states. There's measurement device independent assemblages. There's Bob with input assemblages. So these are also generalized forms of steering. There's distributed ensemble preparations. And then there's bipartite no signaling quantum channels. So all of these have been studied in the literature, and it raises the question, is this exhaustive? Are these the only types of non-classicality in a bipartite common cause scenario? And the answer is no. There are 5 new non-trivial types of bipartite non-classicality that, to my knowledge, no one have studied before. So here's what they look like. And this raises an interesting open question. Do any of these have any deep foundational significance, like entanglement, non-locality, and so on? Or perhaps are they connected to some operational tasks, like quantum information processing protocols? I'm not sure yet. So those are the types of resources. They're all different types. And I want to subsume them all into a single resource theory. So I'll call it the type-independent resource theory. And we need to determine the set of free operations, because the structure of a resource theory is entirely determined by these free operations. How do you choose your free operations? Well, you look at the physical constraints in the scenario that you're trying to study, which here were pretty clear. We said there are no cause-effect relationships between the parties, so there's no communication between them. They're locally unrestricted, and we haven't restricted their common causes. So if we allow the local quantum operations and the classical common causes for free, then it follows that anything which is non-free must require a non-classical common cause. So that's the idea here. Classical common causes will be free. Another word for a classical common cause is shared randomness. That's more common terminology. So I'll term the free operations local operations and shared randomness, or LOSR for short. So we're studying the non-classicality of common cause as the unifying type of resource in all these scenarios. So what are the free LOSR resources? Well, they're the ones that are generated by or can be simulated by local operations and shared randomness. So the local operations get you arbitrary tensor products of channels, and then the shared randomness gives you convex mixtures of those. So any mixture of local operations can be implemented, and any LOSR resource that decomposes in this manner is LOSR free. So let's look at the special case of states, which have no inputs and they have quantum outputs. Then this specializes to this decomposition of the state. And you can see that this is exactly the set of separable states. So we have tensor products of states and then mixtures of those. So the LOSR divide between free and non-free is the same as that between separable and entangled states. What about for boxes? Well, for boxes, all the inputs and outputs are classical. So a box is LOSR free if it decomposes in this form. And this is exactly the set of local boxes, the ones that don't violate Bell inequalities. Because you can imagine, essentially, this is a classical hidden variable that's being copied and sent to the two parties, and then classically processed to give the correlations that are observed. So we're also reproducing the divide between local and non-local boxes. What about for assemblages? Well, again, we reproduce the divide between the unsteerable ones and the steerable ones. For teleportages, we reproduce the divide between the classical ones and the non-classical ones. And you go down the list of all these types of resources that have been studied in the literature, and you look at the ones that are LOSR free versus non-free, and it's exactly that set which has been determined in the past as the ones that are useless or the ones that are valuable, or the ones that are classical and non-classical. So qualitatively, we've reproduced all these types of resources in our resource theory in the way we'd expect. But we want to go further and we want to quantify resourcefulness. And to do that, we need to talk about the free transformations. So if we start with some resource here with some arbitrary input and output types, the most general thing that Alice can do to convert her channel to another channel is called a comb, as first introduced in this paper here, where you pre-process the input to the channel, you post-process the output to the channel, but there can be a side channel as well. So this is called a comb. Alice and Bob can each implement their arbitrary local combs, and then they can use their shared randomness to coordinate their choice of local combs. And this is the most general transformation from some arbitrary type of resource to some other potentially different type of resource. So I want to note that these are type-changing operations in general. So in particular, these input and output types of the initial resource in black need not be the same as the types of those of the effective final resource in green. It just depends on the nature of these local operations done in each lab. So that's how we do free transformations from one type of resource or from one particular resource to another, potentially changing the type. And now we say the value or non-classicality of a resource is fully determined by which conversions are possible and which ones are not. So a resource R is at least as non-classical as another one, R prime, if R can be freely converted to R prime. So this captures the idea that whatever you could do with R prime, you can also do it with R just by first turning R into R prime and then proceeding as you had planned anyway. R and R prime are equally non-classical if they're freely interconvertible. And we say that they're in the same equivalence class. R and R prime are incomparable if neither one can be freely converted to the other. So here's a simple example. We see some resources, and we see that R1 is strictly more non-classical than R2 because it can be converted to R2 but not back. And R3 and R2 are in the same equivalence class. They're equally non-classical. Whatever you can do with one, you can do it with the other. R1 and R4 are both maximally non-classical in the sense that no resource can be converted to them, but neither one is more non-classical than the other. They're just incomparable. So there's not a unique maximal resource in this really simple example. And that's pretty generic to resource theories. But now note that these resources are of arbitrary types. So you can start pairwise comparing all these resources, but now we've got states, boxes, assemblages, distributed measurements, etc. And you can compare them all. So that's going to get pretty crazy, as you can imagine. So we need some tools for characterizing the preorder, this type-independent preorder. So the most common tool in most resource theories is a monotone, which is a function from resources to the real numbers that does not increase under free operations. So you can't generate resourcefulness for free. And the new idea is we want to study not just monotones for boxes, not just monotones for states, but type-independent monotones. So functions from arbitrary types of resources to the reals, so that we can compare across different types. And once you've had the idea to do this, it's not hard to imagine how to go about it, because there are a lot of monotones that have appeared in a lot of different contexts. Things like robustness monotones that can be defined for states and for assemblages and so on. So we took, for example, just as a starting point on these type-independent monotones, we took some robustness monotones and we showed that you can define them in a way that they can be applied to arbitrary types of resources. And furthermore, we proved that they behave monotonically even as you change between resource types arbitrarily. So we have these type-independent monotones. I won't focus on the details of them. You can see our paper, but let's look at some examples. Here are 5 resources of 4 different types. So the first resource is the singlet state. The second one is a distributed POVM that was studied in this paper here, and it's defined by taking the singlet and doing some local Bell measurements. Then we've got 2 assemblages here and here, which I'll try to call the fine-grained assemblage and the coarse-grained assemblage. So they're defined by taking the singlet state and implementing one of the poly measurements, depending on some classical measurement setting. So for this third resource here, there's 3 measurement settings, choosing X, Y, or Z measurements. And for the fourth resource, we have 2 measurement settings, choosing either X or Z measurements. And then finally, we have the Cyrilson box, which is the quantumly realizable box that has the maximal violation of the CHSH inequality. So it's defined by taking the singlet and doing some arbitrarily chosen local measurements. So these are 5 resources of 4 different types, and we're going to compare their non-classicality now using these tools. So let me just number them 1 through 5, and let's talk about which ones can be converted into which others. So the singlet can clearly be converted into all of the others because we see that just from the definition here. Each of these others is defined by local operations on the singlet. So 1 can be converted to 2, 3, 4, and 5. What's less obvious, but what we prove in our paper, is this distributed POVM that we consider can be converted back into the singlet. So they're freely interconvertible. They're equally non-classical. And that means in particular, if 1 can be converted to 3, 4, and 5, then 2 can also be converted to 3, 4, and 5, just by transitivity. Another thing that can be done is this fine-grained assemblage can be converted to the coarse-grained assemblage. So this arrow is possible from 3 to 4. And you can do that just by ignoring this third measurement setting. If you never use it, then you've effectively got this coarse-grained assemblage as well. And furthermore, both of these assemblages can be converted to the Cyrilson box just by doing the appropriate local measurement on Bob's side. So we show that these are all possible, and we furthermore show in our paper that no other conversions between these resources are possible. So this picture here tells you everything you need to know about the pairwise non-classicality of these 5 resources. Of course, another way to analyze these same resources would be to consider monotones. So if you take that monotone that we defined earlier, it's defined for all 4 of these types and for arbitrary types. So we can evaluate it on them. Here's what those values are. We can plot this as a kind of cartoon. So you see that the highest value is given to resources 1 and 2, which are both assigned the value 1. And it's not a coincidence that they're assigned the same value, because we said they're equally non-classical. So it had to be that way. Meanwhile, the fine-grained assemblage is assigned a much smaller value, and an even smaller value is assigned to the coarse-grained assemblage and the Searleson box. But note here that the Searleson box is strictly less valuable than this coarse-grained assemblage, and yet they're both assigned the same value. So we see here that this monotone doesn't give us complete information about these resources. It fails to distinguish the 4th and the 5th resource, even though there will be some monotone that does distinguish them. And this is a generic feature in any resource theory in which there's not a total order. You'll need multiple monotones to distinguish all the resources and to determine the preorder. So now I want to talk about converting between different manifestations of non-classicality. This is something we talk about in depth in one of our papers, but here I'm just going to talk about one result that we got, which is we prove a theorem that every non-free resource of every type can be converted into a distributed measurement without degrading its non-classicality. In particular, no matter what bipartite channel you have, you can convert it into one of this type with just classical outcomes, and it will have the exact same amount of non-classicality as the original resource. In other words, you can convert it back into the original resource using free operations. So that's really surprising at face value. This channel here is completely dephasing, and yet whatever channel you give me, I can convert it into some such object such that you can freely convert it back. So it's a really surprising result, but the proof is extremely simple. So say we start with some resource, a channel E, and let's just focus on one of the systems, say the output of Alice. For this theorem to be true, there better be some transformation we can apply that turns this quantum output into a classical output without degrading the non-classicality. And my claim is, here's how you do it. You just apply this local Bell measurement. So this is all being done on Alice's side. You take some new quantum input and you do a Bell measurement and you get some classical outcome. And that classical outcome is this classical output here. And my claim is that this object can be converted back into E for free. So they're in the same equivalence class. To see that, I need to tell you what are the local operations, or LOSR operations, that can be done to get back E from this channel. Well, here's what it looks like. Alice prepares some entangled state phi max, a maximally entangled state, feeds half of it into this Bell measurement, takes the classical outcome and does a correction operation, and she does all this exactly in the way that implements the teleportation protocol. So in other words, there's an effective identity channel from this quantum system to this one. So this whole thing just equals E. And you see here, all that we required were local operations on Alice's partition. So that establishes the theorem. And we can do the same thing for all the other quantum outputs. And then we've established the theorem. So every quantum output can be turned into a classical output in a way that preserves non-classicality. And this has some, this is very interesting foundationally, because it means that this type of non-classicality somehow is able to encode all the other types of non-classicality. But it's also interesting practically, because it means that all resources of all types can be characterized in a measurement device independent manner. So first you just convert whatever resource you're given into one of this type. And now this type of resource, because it doesn't have any quantum outputs, you can characterize these outputs just using classical systems. You don't need well-characterized quantum devices to probe this kind of resource. So that's the practical significance of this result. So everything I've said so far can be found in these first 2 papers here. But I also want to point you to this last paper, Why Standard Entanglement Theory is Inappropriate for the Study of Bell Scenarios. So in this paper, we note that when people study entanglement, it's typically quantified using the idea that the free operations are local operations in classical communication, or LOCC. So this is done in Bell scenarios, it's done in teleportation, it's done in even things like cosmology. The fact that people have used LOCC operations to quantify entanglement has led to a lot of problems in the literature. So for example, there are these so-called anomalies of non-locality, in which if you're trying to generate non-locality, sometimes you're penalized for having lots of entanglement. It's actually more useful to have less entanglement. And that seems pretty bizarre, so it's been termed an anomaly, and it seems to show that entanglement and non-locality are inequivalent kinds of resources. Measures of one and measures of the other are just unrelated, which seems a bit surprising. But what we show in this paper is it's only true because people have been using the LOCC notion of entanglement, which just isn't relevant in the first place. And if you use the LOSR notion of entanglement, so you order your quantum states with respect to LOSR operations, then we see that measures of one and measures of the other are related in really natural ways. The anomalies go away, and there's a really harmonious interplay between entanglement and non-locality. They're no longer sort of inequivalent resources that can't be compared. They're just the manifestations of the same kind of resource, non-classicality of common causes. And you also learn a lot about things like self-testing and genuinely multipartite entanglement and non-locality. So I recommend that paper as well. And that's all I wanted to say. So thanks for your time, and any questions?